Have you ever considered the last whisper of your own consciousness, that final fleeting collection of memories, thoughts, and feelings that makes you uniquely, irreplaceably times you asterisk? Imagine a machine forged not of steel and silicon but of pure scientific ambition capable of capturing that whisper. A device that could scan the intricate bioelectric labyrinth of your mind, mapping every synaptic connection, every quantum flutter of potential, and creating a perfect, flawless duplicate. Not just a record of your personality, not a crude digital ghost, but an exact atom for atom replica of your awareness, ready to be imprinted onto a new vessel or to live on in an infinite simulated heaven after your biological form has faded. This is humanity's ultimate dream of continuity, our most profound rebellion against the finality of existence. It is the promise of teleportation, where you are deconstructed in one location only to be perfectly reconstructed light years away an instant later. The original is gone, but the copy is so perfect, so complete, that the stream of your consciousness is unbroken. To you, it would feel like blinking. One moment you are gazing at the red plains of Mars. The next you are breathing the methane-laced air of a moon orbiting Saturn, your identity, your very soul ferried across the void on a beam of data. This fantasy of perfect replication extends beyond the self-touching every facet of our ambition. Imagine a universal constructor, a machine capable of duplicating any object. A priceless work of art could be shared with billions, each copy indistinguishable from the original down to the quantum state of every pigment molecule. A life-saving drug complex and difficult to synthesize could be replicated instantly, ending plagues and alleviating suffering worldwide. We could copy endangered organisms, preserving their unique genetic information, not as a frozen sample in a vault, but as living, breathing creatures. The very concepts of scarcity, of loss, of irreplaceability would begin to dissolve in the face of this ultimate technology. It is a future that has been the beating heart of our science fiction for a century, a vision of mastery over the physical world, so total, so absolute, that it borders on the divine. We see this vision as the logical endpoint of our technological evolution, the inevitable summit we are destined to conquer. We have learned to copy the written word, the captured image, the recorded sound. We have decoded and duplicated the very blueprint of life, the DNA molecule. Each step has brought us closer to this grand ideal of perfect fidelity, and it seems only a matter of time and ingenuity before we bridge that final gap between a very good copy and a perfect one. But what if this future is a mirage? What if the universe at its most fundamental level has already issued a final unappealable verdict against this dream? There exists a law not written in the statutes of humankind, but woven into the very fabric of reality itself. It is not a technological hurdle we might one day overcome, nor is it a complex engineering problem awaiting a clever solution. It is a cosmic prohibition, as fundamental as gravity, as absolute as the speed of light. This law acts as a silent, invisible gatekeeper, standing guard over the innermost secrets of existence, and its decree is simple, elegant, and utterly devastating. You cannot create a perfect independent copy of an arbitrary unknown quantum. To state, this is the universe's final veto. And it means that the dream of perfectly copying the intricate quantum information that defines a conscious mind, or the precise state of a single complex molecule, or even just one solitary unobserved particle is and always will be impossible. This profound cosmic restriction is known as the No Cloning Theorem. The name is deceptively simple, almost mundane, yet it represents one of the deepest and most startling truths to emerge from our exploration of the quantum world. It shatters our classical intuition about the nature of information. In our everyday world, information is a passive entity. You can read this sentence, understand its meaning, and then write it down again, creating a perfect copy. The original sentence is unaltered by your act of observing and duplicating it. A sculptor can measure every contour of a marble statue and with enough skill carve a visually identical twin. The information defining the statue's shape is public, accessible, and robust enough to survive the process of measurement. We instinctively believe this principle holds true for everything, that if we could just build sensitive enough instruments, we could measure any object with perfect precision and then use that data to construct a flawless replica. This assumption, this bedrock belief in the passive observability of the world, is precisely where our intuition fails us so spectacularly. Down in the shimmering, uncertain realm of quantum mechanics, the rules are profoundly different. A quantum particle, an electron, a photon, a single atom, does not possess the solid, well-defined properties we are accustomed to. Before it is measured, it exists not as a simple point with a definite location, but as a haze of possibilities, a wave of probability described by its quantum state. This state contains everything there is to know about the particle, its potential energy, its likely momentum, the orientation of its intrinsic spin. It is the particle's informational soul, and here is the crux of the paradox. To copy this soul, you would first need to read it perfectly. But the very act of observing a quantum system, of asking it a question, "Where are you? What is your spin?" is not a passive glance, it is an intrusive, transformative event. The moment you measure an unknown quantum state, you inevitably and irrevocably change it. That delicate wave of possibilities, holding an infinity of potential answers, collapses into a single concrete reality, a single piece of classical information. It's like trying to capture the exact form of a soap bubble by touching it. The moment your finger makes contact, the beautiful iridescent sphere is gone, leaving behind nothing but a droplet of soap. The information you sought to measure is destroyed by the very act of measurement. The whisper of quantum potential is silenced, replaced by the shout of a classical fact. This is not a failure of our technology. You cannot build a more delicate measuring device to get around this problem. The disturbance is built into the fundamental grammar of the universe. It is a consequence of the Heisenberg uncertainty principle, which dictates a trade-off in what we can know simultaneously about a particle. The more precisely you know its position, the less precisely you know its momentum, and vice versa. Any attempt to extract the full information of a quantum state is like trying to see both sides of a coin at the same time. It is a logical and physical impossibility. So how could you possibly clone something you are forbidden from ever knowing completely? If you cannot perform a full scan of the original without destroying the very information you wish to copy, the entire enterprise is doomed from the 18. Start. The universe has essentially encrypted its own fundamental data. It allows us to glimpse pieces of it to force an answer to a specific question, but it forbids us from ever possessing the entire unadulterated blueprint of an unknown quantum state. A perfect copy would require a perfect knowledge of the original, and perfect knowledge is a privilege the quantum realm never grants. This theorem draws a stark, uncrossable line in the sand. On one side lies the classical world of big, sturdy objects, where information can be copied freely, where scarcity is an economic problem, and where loss, while painful, is not always absolute. On the other side is the quantum world, the foundation of everything we see, a world governed by a fierce, almost jealous protection of originality. In this world, every unmeasured quantum state is a unique, singular entity. Its information is a private, confidential affair between it and the universe. The No Cloning Theorem is the guardian of that privacy. It ensures that the quantum realm cannot be trivially xeroxed, that the fundamental building blocks of reality retain their enigmatic integrity. It transforms our understanding of information itself from a simple abstract quantity to a potent physical thing, subject to profound and inviolable laws. It implies that at the very bottom of reality, there is a form of ultimate, unbreachable uniqueness. The implications of this are staggering, and they ripple outwards, touching upon the very future of our civilization. The dream of teleportation as a copy and paste process for human consciousness is not just science fiction, it is a physical impossibility. To scan your quantum state would be to destroy you, and without that perfect scan, no perfect copy could ever be made. Any functional teleporter would have to be something far stranger, perhaps a machine that somehow moves the original intact through a wormhole or some other distortion of space-time. The notion of backing up your mind to a hard drive, creating a perfect digital spare, is also relegated to the realm of fantasy. The best we might ever hope for is a classical approximation, a brilliant simulation, but it would not be a true copy. It would not be times U asterisk. The theorem places a fundamental limit on our ability to cheat death to duplicate identity, to erase the sting of final loss through perfect replication. It bestows upon every conscious being, every complex living thing, a kind of quantum-ensured sanctity and inherent irreplaceability. Your specific quantum arrangement is yours, and yours alone, a fleeting masterpiece that can never be perfectly recreated once it is gone. Yet this cosmic no is not merely a restriction. It is not the universe simply thwarting our grandest ambitions out of spite. Like all great physical laws, the No Cloning Theorem is two-sided. While it closes the door on one set of dreams, it unlocks a new universe of possibilities that would be impossible without it. This very limitation is the bedrock upon which the future of computation and communication is now being built. The fact that a quantum state cannot be copied without being disturbed is the ultimate guarantee of security. It allows for the creation of unhackable communication channels, quantum cryptography systems, where any attempt by an eavesdropper to intercept a message would inevitably leave a detectable trace, a smudge on the quantum state. The eavesdropper, in trying to copy the information, would be forced to measure it, thereby destroying the original state and immediately revealing their presence. It's as if every secret letter were written in an ink that vanishes the moment an unauthorized person lays eyes on it. This theorem turns a seeming weakness of the quantum world, its fragility, into its greatest strength, promising a future of perfectly secure information exchange. Furthermore, this principle is deeply entangled with the very power of quantum computing. A quantum computer derives its extraordinary potential from the ability of quantum bits or qubits to exist in a superposition of states, exploring a vast landscape of solutions simultaneously. The No Cloning Theorem is essential for preserving the integrity of these delicate superpositions. If you could easily clone qubits, you could cheat the uncertainty principle, making 1,000 copies of a particle and then measuring a different property on each one to build up a complete picture of its original state without disturbing it. This would violate the very foundations of quantum mechanics and dissolve the advantages that quantum computers possess. The inability to clone is what protects the strange parallel processing power of the quantum realm, allowing it to perform calculations that would take a classical computer longer than the age of the universe to complete. The barrier is in a profound sense the source of the magic. The universe's refusal to be copied is what makes it so powerful, and so we find ourselves standing at the edge of a great mystery. We are confronted by a law that feels deeply counterintuitive, a law that blesses every fundamental particle with a unique, inviolable identity. It protects our secrets, empowers our future technologies, and forces us to reconsider the very nature of what it means to be an individual. But it leaves us with the most tantalizing question of all. Why times? Why is reality structured this way? Why would the universe forbid such a seemingly simple and useful act as duplication at its most fundamental level? Is this a mere accident of the mathematical framework of quantum mechanics, a quirky byproduct of the equations? Or does the No Cloning Theorem point to a deeper, more profound truth about the nature of information existence and the flow of time? What does this cosmic rule protect? What chaos does it hold at bay? To answer this, we must journey deeper into the quantum realm, a world where reality is painted not in certainties but in probabilities, where particles can be in many places at once, and where the future is an open vista of shimmering potential. We must explore the very logic that underpins existence to understand not just what the rule is, but the reason for the rule. For in understanding why we cannot copy the universe, we may finally begin to understand the universe itself. What does it mean to truly copy something? Not just to approximate it or to create a convincing forgery, but to craft an identical twin, perfect in every detail, indistinguishable from the original down to its very soul. In our world, the world we see and touch, this act of duplication has become the defining rhythm of our civilization. It is the engine of progress and the bedrock of memory. Think of the first scribe painstakingly transcribing a sacred text, every stroke of the stylus an attempt at perfect fidelity, or the printing press democratizing knowledge by stamping out legions of identical pages, each one a faithful echo of the last. Today, in our digital age, this process has achieved a kind of godhood. You hold in your hand a device that can capture a fleeting moment, the light from a loved one's smile, and translate it into a language of ones and zeros, a simple, unambiguous code. This string of data, this digital photograph, is classical information. Its defining characteristic is not its beauty, but its resilience, its willingness to be copied. You can send this file across oceans in an instant. You can upload it to a cloud, where it is mirrored on countless servers, a constellation of perfect replicas scattered across the globe. You can download it, save it, edit it, and share it again, and with every single transmission, every duplication, the copy is flawless. The ones remain ones and the zeros remain zeros. The information is robust, definite, and profoundly public. It can be read without being disturbed, measured without being altered. This very idea that information can be observed and copied without penalty is so deeply woven into the fabric of our experience that we mistake it for a fundamental law of reality. We have built our entire world on this assumption. Every book in every library, every byte on the internet, every gene in a DNA sequence all seem to shout the same truth: what can be known can be copied. But this world, this comfortable classical reality, is a facade. It is a grand, sweeping illusion painted over a much deeper, stranger, and more delicate canvas. Beneath the certainty of our everyday existence lies a realm where information behaves not like a chiseled stone tablet, but like a whispered secret, a phantom that vanishes the moment you shine a light on it. This is the quantum world, and in this world, the simple act of looking changes what you see. Here the fundamental currency is not the bit, the unambiguous on or off, but something far more ethereal, the quantum bit or qubit. A classical bit is like a light switch. It is either on or it is off. It has a definite state, a single unwavering answer to a question. A qubit, however, is a storm of possibilities. It is a spinning coin caught in the air, not yet heads and not yet tails, but a blur of pure potential containing both outcomes at once. This bizarre and beautiful state is called superposition. It is not a state of ignorance where we simply don't know the answer. It is a state of genuine multiplicity, where the qubit truly is both 0 and 1 simultaneously held in a fragile probabilistic balance. It occupies a ghost-like existence, a spectrum of maybes. All the power, all the magic of the quantum realm is born from this uncertainty. Imagine trying to describe the precise location of a single wave in the ocean. You can't. The wave is not a point, it is a distributed flowing entity. A qubit is much the same, a wave of information, its identity spread across a landscape of potential realities until you measure it. The moment you interact with it, the moment you ask, are you a 0 or a 1, the spinning coin falls. The wave of possibility collapses into a single definite point. The shimmering superposition is shattered, and the qubit is forced to choose a classical identity, becoming a mundane bit just like any other, and in that collapse the magic is lost. The rich, multi-layered quantum information it once held, the symphony of probabilities, evaporates into a single dull note. You learn its state, yes, but at the cost of destroying the state itself. It is a cosmic catch-22. To know the quantum world is to break it. This inherent fragility is the source of its immense power. A computer built on classical bits like the one you are using now must check every possibility one by one, a laborious linear march. If a problem has 1,000,000 possible solutions, it must perform 1,000,000 calculations. But a quantum computer harnessing the power of superposition can embody all those possibilities at once. A handful of qubits existing in this state of multiplicity can explore an entire universe of potential solutions simultaneously. They create a computational space so vast it dwarfs the number of atoms in the known universe, a parallel reality where every path is walked at the same time. This is the promise that keeps scientists awake at night, the ability to design revolutionary new medicines atom by atom, to create materials with impossible properties, to unlock the deepest secrets of cosmology and consciousness. All of it resting on the delicate shoulders of these undecided states. But superposition is only the first chapter of this strange story. Quantum mechanics has an even more profound, more unsettling secret, a phenomenon so bizarre that it haunted its own discoverers. It is a mystery that binds the fates of particles across any distance, a connection that seems to violate the very speed of light. It is called entanglement. Imagine you have two of our spinning coins, our qubits, but these two are special. They have been forged together in a quantum fire, their fates inextricably linked. They now exist in a single shared state of being. You can hold one in your hand and send the other to the far side of the galaxy. They are separated by an impossible chasm of space and time. Yet they are not separate entities. They are two parts of a single whole. A single story told across two cosmic volumes. When you finally force the coin in your hand to land, to choose between heads or tails, something extraordinary happens. At the very instant of your measurement, you know with absolute certainty the state of its distant twin. If your coin lands on heads, its partner light years away instantaneously becomes tails. There is no signal sent, no message traveling through the void. It is a ghostly immediate correlation, a shared destiny. This is not a matter of a predetermined outcome like two gloves separated into two boxes. In that classical case, the identity of each glove was fixed from the beginning. With entangled particles there, times is times, no predetermined outcome. Both qubits remain in a shared, indefinite superposition, a haze of combined possibilities until the very moment one is measured. It is the act of observing one that instantly defines the reality of the other, as if they are two ends of a single invisible gravitational gyroscope where pushing one side down simultaneously and instantly lifts the other regardless of the distance between them. This bizarre and unbreakable bond is not just a theoretical curiosity. It is the foundation for the future of secure communication. Imagine encoding a message in a stream of these entangled particles. You and your intended recipient share the linked pairs. Because their states are perfectly correlated, you can create a key that is fundamentally physically private. The laws of quantum mechanics themselves become your security guard. If an eavesdropper were to intercept one of these particles and try to measure it, their very act of observation would shatter the delicate entanglement. It would be like a burglar tripping a laser wire made of reality itself. The disturbance would be immediate and obvious. The secret message would be protected not by a clever password, but by the fundamental structure of the cosmos. Here, the fragility of the quantum state, once a challenge to be overcome, is transformed into its greatest strength. The whisper that vanishes when you listen too closely becomes the ultimate shield. So now we stand at the threshold of a new epoch. We have glimpsed a hidden layer of reality, one teeming with power. We see quantum states that can hold entire libraries of information in the space of a single particle. We see connections that defy our understanding of space and time, offering the promise of perfectly secure channels of communication. We see the potential for computers that can solve problems currently beyond the grasp of all human endeavor. The key to this future, the very soul of this new machine, is the quantum state itself. The precise, delicate, and multi-layered arrangement of superposition and entanglement across a collection of qubits. This state is the software. It is the algorithm. It is the answer. And having created such a state, having painstakingly engineered this fragile tapestry of quantum information, an incredibly powerful and profoundly human desire emerges. The desire to protect it, to safeguard it, to make a backup. In our classical world, this is the most natural impulse. If you write a brilliant piece of software, you make copies. If you have a critical piece of data, you store it in multiple locations. Redundancy is safety. Duplication is preservation. So why should the quantum world be any different? If we manage to configure a set of qubits into a state that could, for example, simulate the creation of a life-saving drug, the value of that single fleeting quantum state immeasurable. Losing it to the slightest environmental disturbance, to a stray magnetic field or a random photon, would be a catastrophic failure. The only sensible path forward would be to copy it, to create a perfect quantum clone, an identical replica of that precious state, so we can protect our work, verify our results, and build upon them. We must want to build a quantum photocopier. A machine that can take an arbitrary unknown quantum state as an input and produce 2 or 10 or 1,000 perfect identical copies as output without disturbing the original. This is not just a convenience, it feels like a necessity. It feels like the only way to build a scalable, reliable quantum technology. The entire architecture of classical computing relies on the ability to copy bits effortlessly from one part of the machine to another. How could we possibly hope to build its quantum successor without this most fundamental of operations? The universe, it seems, has handed us a key of unimaginable power, but fashioned it from the most delicate, brittle glass. The urge to forge a stronger one to duplicate it before it shatters is overwhelming. It is logical, it is intuitive, it is, however, utterly and completely impossible. So we are here at the precipice of a revolution. We have conceived of a machine, a quantum duplicator built not from gears and steel, but from the very laws that govern the heart of matter. Its purpose is simple, its promise godlike, to take a single unknown quantum state, the soul of a particle, and forge a perfect, indistinguishable twin. The implications ripple outwards, promising invulnerable communications, computers of unimaginable power, even the ability to recreate a moment in time if only we could capture its quantum essence. But as we reach out to grasp this power, we find our hand passing through it like a phantom. A fundamental principle of reality itself, silent and absolute, stands in our way. This is not a technological hurdle we can simply engineer our way around. It is a direct confrontation with the most intimate and paradoxical rule of the cosmos. To understand why, you must first forget everything you know about copying. Cast your mind to the most basic act of duplication in our classical world. A photocopier. It seems trivial, almost mundane. You place a document on the glass. A brilliant light scans across the page, a mechanical eye discerning patterns of black and white shades of grey. This information, this map of ink on paper, is translated into a simple binary code. The machine then commands a tonodrum to replicate that exact pattern on a blank sheet. It is an act of observation followed by recreation. The key, the absolute linchpin of the entire process, is that the observation is passive. The original document is bathed in light, but it emerges from the machine, fundamentally unchanged, ready to be copied again and again, 1,000 times, 1,000,000 times. It knows nothing of the scrutiny it has just endured. This is the classical dream, the assumption we carry in our bones, that to know something is not to change it, that we can be silent observers, perfect witnesses to the universe. Quantum mechanics laughs at this assumption. In the quantum world, there are no silent witnesses, there is no passive observation, there is only interaction. To see, to measure, to times no times, a quantum system is to intrude upon it, to ask it a question so forceful that the asking irrevocably alters the answer. Imagine you are presented with a sculpture of unimaginable intricacy and fragility, a form spun from smoke and held together by a whisper. Your task is to describe its exact shape. But your only tool is your hand. The moment you reach out to feel its contours, the very instant your fingers make contact, the smoke swirls. The delicate form collapses, dissipating into a simpler, coarser shape. You have learned something times about it, perhaps its general size, its temperature, but in the act of learning, you have annihilated the very masterpiece you sought to understand. The original, with all its subtle, ghostly complexity, is gone forever. This is the violent heart of quantum measurement, and it is the first dagger in the heart of our quantum cloner. Let us walk through the crime scene of a failed attempt. In our laboratory, we have our target qubit A. It is a single particle, an electron perhaps existing in a state of pure quantum potential. It is not merely spin up, nor is it spin down. It is in a superposition, a delicate blend of both possibilities at once. Think of it as a spinning coin forever in the air, a perfect balance of heads and tails. The specific balance, the precise mixture of up and down, is its unique identity, its secret. This secret is what we want to clone. We do not know the mixture. It could be 70% up and 30% down. It could be 50-50. It could be any infinite variation in between. This unknown state is our message in a bottle. Next to it, we have qubit B. This is our blank canvas, our unwritten page. We have prepared it in a simple known state, say 100% spin down. Our hypothetical cloning machine is the intermediary, the forger's tool. Its job is to read the state of qubit A and imprint it perfectly onto qubit B. The process begins. The The machine must first gather information. It must interrogate qubit A. It must ask the ultimate question, what are you? It performs a measurement. But remember, a quantum measurement is not a gentle inquiry. It is a demand. It forces the qubit to choose. The universe itself intervenes and compels our spinning coin to land. In that cataclysmic instant, the superposition shatters. The infinite potential collapses into a single mundane reality. Let's say the coin lands heads up. Our qubit A is now definitively 100% spin up. Take a moment to grasp what has just been lost. The secret is gone. The original delicate 70-30 blend, the unique soul of the particle, has been wiped from existence. All that remains is the brute fact of the outcome. The smoke sculpture has been touched and has collapsed into a simple puff. The machine, however, registers the outcome. The particle is spin up, it concludes. The first step of the cloning process, the act of reading the information, has resulted in the complete destruction of that very information. But the machine, unaware of this cosmic tragedy, dutifully proceeds. It now has a piece of classical information up. It turns to our blank canvas qubit B and performs a simple operation. It flips qubit B from its initial spin-down state into a spin-up state. The task seems complete. We look at our result. We have qubit A, which is now spin-up, and we have qubit B, which is also spin-up. They are identical, but are they a clone of the original? Absolutely not. We have failed. We have not cloned the mysterious ghostly superposition. We have not duplicated the spinning coin. We have merely taken a photograph of the coin, times after times it has landed, and then created a second photograph of the same outcome. We started with one particle holding a universe of potential and ended with two particles locked into a single brute actuality. This is not cloning. This is a clumsy, destructive caricature. It is like reading the last page of a novel, learning who the killer is, and then writing that name on the cover of 100 blank books. You have copied the conclusion, but you have utterly failed to replicate the story, the suspense, the nuance, the very essence of the thing you sought to preserve. Every attempt will end in this same catastrophe. If you measure in a different basis, a different orientation, the same collapse occurs. The superposition is a sacred, private thing. The moment you demand it reveal itself publicly, it vanishes, leaving behind only a pale shadow of what it once was. This is the No Cloning Theorem in its most visceral form. It is not that our machines are too crude. It is that the universe itself has decreed that certain information can only be held by a single possessor at any one time. This principle is so profound, so deeply stitched into the fabric of reality, that it arises from the most fundamental mathematics describing our universe. Quantum mechanics at its core evolves according to a beautiful and relentless rule known as linearity. It means that the evolution of a quantum state over time is smooth, continuous, and respects superposition. If you start with a combination of two states, the system will evolve into the same combination of those two states' futures. It's a law of preservation. The quantum wave function, governed by the Schrödinger equation, flows like a perfect, incorruptible river. It can be diverted, it can be split, but its fundamental nature cannot be arbitrarily remapped. A hypothetical perfect cloning machine would be a violator of this sacred linearity. Think of what we are asking it to do. We are demanding a single process that can take times, any times unknown input state, let's call it psi, and an adjacent blank state, and transform them into two identical copies of psi. It must work universally for every possible psi we feed it. Mathematicians, however, have proven that no such universal transformation is compatible with the linear flow of quantum evolution. To create such a machine would require a process that could somehow look at two different initial superpositions, say a 70-30 mix and a 50-50 mix, and treat them differently, amplifying their properties in a non-linear way. This would be like asking a prism to bend red light dramatically but leave blue light completely untouched. A prism cannot do that. It treats all light according to the same fundamental rules of refraction. Its effect is linear. In the same way, the universe cannot evolve a quantum state in a way that selectively duplicates its information content. The river of quantum time simply cannot flow in the way a cloner would demand. The theorem is not just an observation about measurement, it is a direct consequence of the underlying grammar of reality. The universe does not speak the language of duplication. But what if we try to be more clever? The astute physicist might argue that we don't need to measure so brutally. Perhaps we can coax the information out. We could try to use the gentle, ghostly touch of quantum entanglement. Let's imagine our cloning machine is designed not to measure qubit A directly, but to entangle itself with it. Entanglement, as we've seen, is that strange connection where two or more particles become linked, their fates intertwined into a single shared state of existence, no matter how far apart they are. So our new plan is this. We take our original qubit A, our blank qubit B, and a third particle that is part of our cloning apparatus, qubit C. We then perform a complex operation that entangles all three of them. The goal is that this three-body entangled state will somehow contain the information of qubit A, which we can then gently transfer to qubit B. We are trying to build a bridge of entanglement to ferry the quantum secret across. For a breathtaking moment, it seems like it might work. We have created a complex, unified quantum object, a single state describing all three particles at once. The original information from qubit A is no longer localized to it alone. It is now smeared out, distributed across the entire entangled system. But now we face the final insurmountable hurdle. The information is spread across the triplet, but it is not copied onto qubit B. Qubit B is not an independent clone. It is now a prisoner, locked in a complex relationship with the other two particles. To complete the cloning, we would have to somehow disentangle qubit B from the others, leaving it in the perfect state of the original A. And how do we do that? How do we sever the connection and read out the state to confirm our success? We must once again perform a measurement. And the moment we do, the instant we ask the system for any information about qubit B's state, the entire fragile three-body superposition collapses. The entanglement shatters, the ghostly connection vanishes. And we are left with exactly what we had before, not a pristine clone, but a random classical outcome, a graveyard of lost potential. Entanglement, far from being the solution, becomes the ultimate illustration of the problem. It shows that quantum information is holistic. You cannot isolate one part and duplicate it without affecting the whole. The universe does not permit this kind of selective forgery. It's like trying to copy a single ripple in a pond. You cannot lift the ripple out of the water. Its very existence is defined by its relationship with the entire surface. The act of trying to isolate it destroys it. The secret of the qubit is not merely times in times the particle. It times is times the particle in its unique, untouchable, and ultimately solitary state of being. We must therefore abandon our classical intuition entirely. The No Cloning Theorem is not a cosmic denial, a limitation imposed upon us by a stingy universe. It is a fundamental feature that gives quantum mechanics its very character. The impossibility of cloning a quantum state is the flip side of the coin to its absolute security. Because a state cannot be copied without being disturbed, it means that any attempt by an eavesdropper to intercept a quantum message will inevitably leave a trace. The spy, in trying to copy the information, destroys it, alerting the legitimate recipients. This fragility is its armor. The whisper that cannot be copied is also the whisper that cannot be secretly overheard. This confrontation, this failed attempt to become quantum counterfeiters, forces us to a humbling and profound realization. We began this journey with a very human desire to possess, to replicate, to control. We wanted to take the most fundamental unit of information in the universe and make it our own, to print it out on demand. But the universe has taught us a lesson in humility. It has shown us that some things are unique by their very nature. The quantum state is not a string of data to be copied and pasted. It is a singular, ephemeral existence. We stand in the wreckage of our cloning machine, but we are not defeated. We are illuminated. We have discovered a new boundary of reality, a law as fundamental as gravity. We have learned that to truly know a quantum secret is to become its sole keeper, for the act of sharing it through duplication is an act of annihilation. The original masterpiece can never be recreated, only remembered as a single data point, a ghost of its former glory. We came seeking to duplicate reality, but instead we discovered a far more profound truth. Some things in this universe are meant to be unique, and in that uniqueness lies a power we are only just beginning to understand. A power not of duplication but of transformation, a power that leads not to endless copies but to a mystery even more tantalizing than cloning itself. And so the paradox was set, a universe built on information, yet a universe that seemed to guard its most fundamental secrets with an almost jealous possessiveness. We had learned to read the quantum book of life, to glimpse its strange and beautiful language of probability waves and superposition, but we were forbidden from making a copy. This wasn't a technological hurdle we had yet to overcome. It felt like a cosmic veto, a law written in the fabric of space-time itself, yet a law for which no one had yet found the scripture. The question hanging in the air of physics laboratories across the world was no longer simply times how, times, to copy a quantum state, but a far more profound and unsettling one. Times why, times was the universe so profoundly opposed to the POW idea. The answer, when it came, would not arrive as a single, earth-shattering thunderclap. Instead, it would emerge as a quiet, almost simultaneous whisper from different corners of the intellectual world, a testament to an idea whose time had irrevocably come. The dawn of the 1980 seconds was a period of intense theoretical fermentation. The foundational pillars of quantum mechanics erected half a century earlier were being tested not with particle accelerators, but with thought experiments of dazzling ingenuity. It was a time for asking deceptively simple questions that exposed the deepest architectural truths of reality. In the quiet halls of academia, minds were turning over this very problem of duplication. It was a puzzle box, and everyone who touched it felt the same strange resistance, the same internal logic that seemed to slam the lid shut the moment you thought you had it pried open. The stage was set for the mystery to be formalized, to be translated from a nagging intuition into the unyielding language of mathematics. And the protagonists of our story were not grand collaborators on a single project, but independent intellectual explorers who, separated by geography, arrived at the same astonishing destination. In one corner, we find two brilliant minds converging at the University of Texas at Austin, William Wouters and Wojciech Zurek. They were wrestling with the implications of quantum measurement, particularly the way an observation irrevocably alters the system being observed. This principle, the observer effect, was the original ghost in the machine, the first clue that quantum information was slippery, that it couldn't be known without being changed. They were probing the limits of what we could learn about a quantum system. If you receive a single unknown quantum particle, say a photon polarized in a specific but unknown direction, what is the maximum amount of information you can extract from it? The obvious classical answer would be to measure it, learn its polarization, and then create millions of identical photons. But quantum mechanics recoils from this idea. A single measurement collapses its wave function, forcing it to choose a state and destroying the delicate superposition it once held. The original unknown state is gone forever, replaced by the outcome of your measurement. This destructive nature of measurement was the breadcrumb trail they followed. The thought process became a relentless cascade of logic. If you cannot perfectly determine an unknown state with a single measurement, perhaps you could find a clever workaround. What if instead of measuring it directly, you could first create a perfect replica, an exact duplicate? Then you would have two particles in the identical unknown state. You could keep one pristine, a perfect reference copy while you performed your disruptive measurement on the other. With the first copy destroyed by measurement, you would still have the second untouched and identical to the original. You could then repeat the process, creating a second clone from your remaining original, measuring that one, and so on. You could, in theory, generate an infinite ensemble of identical particles, allowing you to map the original unknown state with arbitrary precision. You would have effectively circumvented the uncertainty principle itself. You would have beaten the house. This was the intellectual precipice. Wouters and Zurek realized that such a cloning device would represent a fundamental backdoor in the architecture of quantum reality. It would break the most sacred rules. It would allow you to know the unknowable. And for physicists, when a hypothetical process leads to the violation of a core principle like uncertainty, it's not a sign of a brilliant new invention. It is a sign that the hypothetical process itself must be impossible. The universe does not permit such loopholes. Their task then was to prove it. They set out to construct on paper the most perfect, most powerful, most general quantum copying machine imaginable. They didn't encumber it with technical details of lasers or magnetic fields. They treated it as a pure mathematical operator, a function whose sole job was to take one quantum state as an input, along with a blank target state, and produce two identical copies of the original as an output. Here, they ran headfirst into the most fundamental and non-negotiable law of quantum evolution, linearity. It's a concept that sounds abstract, but its consequences are earth-shattering. Linearity essentially means that if you do something to a combination of states, the result must be the same as if you did it to each state individually and then combined the results. Think of it as a law of fairness for quantum possibilities. If a quantum system is in a superposition of state A and state B, any physical process acting on it must act on both A and B simultaneously and without prejudice. This mathematical rigidity is what allows quantum waves to interfere, to cancel each other out or amplify one another. It is the engine of all quantum computation. It is the bedrock. Wouters and Jurek applied this inexorable law to their hypothetical cloning machine. Imagine your unknown particle is a qubit, and its state is a superposition of 0 and 1. Let's call this state psi. The cloning machine is supposed to take psi and a blank state, let's say blank, and output two copies, psi, psi. That's its only job. So if you feed it a pure 0, it must dutifully produce two zeros, 0, 0. If you feed it a pure 1, it must produce two ones, 1, 1. So far, so good. The machine seems to work perfectly for these simple, classical-like basis states. But the soul of quantum mechanics lives in superposition. What happens when you feed the cloner the truly quantum state, the one that is a mix of both, say, .0 plus .1? This is where the universe slams the door shut. Because of linearity, the cloning machine must operate on the 0 part and the 1 part of the superposition independently. Applying the cloning process to the combined state, 10, 0 plus 1, must yield the sum of the results of cloning each part separately. Cloning the 0 part gives you 0, 0. Cloning the 1 part gives you 1, 1. Therefore, linearity dictates that the final output times must times be a superposition of these two outcomes, 0 plus 1, 1. Now look closely at what we have. This is not what we wanted. We wanted two separate, identical copies of the original state. We wanted 0 plus 1 multiplied by 0 plus 1. If you do that multiplication, you get a much more complex expression. 0, 0, plus 0, 1, plus 1, 0, plus 1, 1. The two results are mathematically fundamentally irreconcilably different. The state the machine times actually times produces 10, 0 plus 1, 1 is a bizarre and fascinating state of its own. It's a profoundly entangled state, a Bell state. The two output particles are now linked in a way that transcends classical understanding. They are not independent copies. They are a single unified system. Measuring one instantly determines the state of the other, no matter how far apart they are. The machine didn't create a clone. It created an inseparable pair, a quantum chimera. It failed. And the beauty of the proof was that it showed that any times such machine, no matter how ingeniously designed, must fail in precisely the same way, because it would always be bound by the axiomatic chains of linearity. In 1982, Wouters and Jurek published their findings in the journal Nature Times in a landmark paper titled "A Single Quantum Cannot Be Cloned." The conclusion was as elegant as it was inescapable. The very mathematical structure that gives quantum mechanics its power, superposition, and linearity is the same structure that erects an impenetrable fortress around its information. You cannot have one without the other. Meanwhile, with an almost poetic serendipity thousands of miles away in the Netherlands, the physicist Dennis Dieks was independently treading the exact same intellectual path. Driven by similar questions about the foundations of quantum theory, He too had identified the conflict between the idea of a universal cloner and the principle of linearity. He published his own similar proof in Times Physics Letters A, Times that very same year. The nearly simultaneous discovery by two separate groups unaware of each other's work was a powerful confirmation that this was not some clever mathematical trick. It was a fundamental truth about nature, a property of our universe that was simply waiting to be excavated from the bedrock of existing theory. The initial reaction in the wider physics community was one of quiet surprise, a collective intellectual jolt. For decades, the impossibility of cloning had been an unspoken assumption, a piece of folklore that everyone knew but no one had bothered to formally prove. It was like discovering a formal proof that you can't build a perpetual motion machine. The outcome was expected, but the elegant finality of the proof changed everything. It transformed a vague, intuitive notion into a theorem as solid and as permanent as the Pythagorean theorem. What began as a question rooted in the esoteric domain of quantum foundations quickly began to ripple outwards, its implications washing over field after field. Initially, it was seen as a profound limitation. A barrier, a cosmic no. You cannot amplify a quantum signal the way you amplify a radio wave because amplification is fundamentally a process of cloning. You cannot create perfect backups of quantum data. You cannot broadcast a quantum state to multiple receivers. This seemed to place a hard ceiling on the dream of quantum technologies. It appeared to be a universe that at its most granular level was inherently private and ephemeral. A single quantum of information was like a soap bubble, a thing of perfect iridescent beauty that vanishes the moment you try to grasp it, let alone copy it. But as the community digested the result, this perspective began to invert. Scientists and engineers, a naturally optimistic and inventive breed, began to look at the theorem not as a barrier but as a gift. They started to ask a different question: if the universe forbids copying, how can we use that prohibition to our advantage? The impossibility of cloning was not a bug, it was a feature, and its most immediate and spectacular application was in the nascent field of cryptography. For millennia, the core challenge of security has been the secret key. How do you share a key for encrypting and decrypting messages without an adversary intercepting it and crucially copying it without your knowledge? Classical information can be passively monitored, copied perfectly, and the original is left none the wiser. Your digital secrets can be duplicated endlessly, leaving no trace of the theft. The No Cloning Theorem, however, offered a radical new paradigm. If you encode your cryptographic key into the quantum states of single photons and send them from Alice to Bob, any attempt by an eavesdropper Eve to intercept and read the key will be governed by this unbreakable law. Eve cannot simply catch a photon, measure its state, and send an identical one on its way to Bob. The moment she measures it, she collapses its wave function, altering it. Even if she tries to be clever and use a hypothetical quantum cloner, we know her machine will fail. It will not produce a perfect copy. It will produce a disturbed, entangled state. In either case, her very act of snooping introduces detectable errors into the stream of photons arriving at Bob's end. Alice and Bob can then publicly compare a small sample of their key. If the error rate is above a certain threshold, they know someone is listening. They can discard the compromised key and try again. The security of their communication is no longer guaranteed by the cleverness of a mathematical algorithm, but by a fundamental law of physics. The No Cloning Theorem had just given birth to quantum cryptography, providing a form of security that is in principle absolute. This shift in perspective from limitation to opportunity was profound. The theorem became a cornerstone, a load-bearing pillar supporting our entire understanding of quantum information. It provided a deep insight into why the universe works the way it does. It helps explain why the bizarre, spooky action at a distance of entanglement cannot be used to send signals faster than light. If you could clone one particle from an entangled pair, you could devise a scheme to learn about its distant twin, instantaneously violating Einstein's cosmic speed limit. The No Cloning Theorem acts as the universe's great policeman, upholding the law of causality and ensuring that information, even quantum information, respects the structure of space-time. More than that, it forced us to confront the very nature of what a quantum state times is, asterisk. It is not merely a description of a particle's properties, like a blueprint that can be copied to build an identical house. The state times is times the particle in a way that has no classical analog. It is a unique and singular instance of reality. Its information is embodied, not just recorded. The theorem tells us that the quantum world is not a world of reproducible objects, but of unrepeatable events. Each quantum state is a fleeting, original masterpiece. To observe it is to change it. To know it is to destroy it. And to copy it is and always will be impossible. This once perceived flaw was now understood as the defining feature of the quantum realm, the very principle that makes it so radically different from our everyday experience. And it raised a tantalizing new question. If we cannot copy a quantum state, if we can't make a perfect replica, is there any times way to move its precious, fragile information from one place to another without losing it forever? The answer would require a journey even deeper into the looking-glass world of quantum mechanics, a journey towards a process so strange, so paradoxical, it sounds like it was lifted directly from the pages of science fiction. A process called teleportation. And so we arrive at a precipice of understanding a stark and seemingly absolute cosmic decree. The universe, in its deepest quantum grammar, has uttered a definitive no perfect copies, no flawless replication of the unknown. It feels like a door has been slammed shut, a fundamental power we imagined for ourselves, the power of infinite duplication revealed as a fantasy. We have travelled through the ghostly corridors of superposition and the dizzying entanglement of distant particles, only to find a universal law that feels less like an opportunity and more like a profound, unyielding limitation. It is a moment that invites a deep philosophical sigh, a recognition that some secrets encoded in the very fabric of reality are meant to be kept. But what if we have been reading the message all wrong? What if this cosmic prohibition isn't a barrier at all? What if hidden within this absolute denial lies the key to an entirely new kind of power, a promise more potent than we could have ever conceived? The journey down this path of seeming restriction may paradoxically be the only way up. Before we follow that path, we must steady ourselves and draw the boundaries of this law with exquisite care. The No Cloning Theorem is not a blunt instrument of cosmic censorship. It is a surgeon's scalpel, precise and specific. It does not forbid all forms of copying, and to believe so would be to misunderstand its beautiful and subtle power. Consider the world you know, the classical world of tangible information. You can photocopy a page from a book, and the new page is for all practical purposes a perfect replica. You can duplicate a digital file, a song, a photograph 1 billion times over, and each copy is indistinguishable from the original. This is possible because the information is classical, its state is known and definite. Each bit is either a 0 or a 1, a simple binary choice that can be read without ambiguity and rewritten without consequence. The act of observing the classical world does not on a meaningful level change it. Even in the quantum realm, this principle holds a certain truth. If we know with absolute certainty the exact quantum state we wish to create, if we possess the complete blueprint, then we are not forbidden from producing it. Imagine a master artisan who knows the precise sequence of steps to create a magnificent quantum sculpture. She can follow her instructions, her blueprint again and again, producing 1,000 identical quantum systems, each one prepared in exactly the same state. This is not cloning, this is manufacturing. She is not copying a mysterious unknown artifact. She is simply following a known recipe. The No Cloning Theorem is entirely unconcerned with this process. Its jurisdiction applies only to the unknown. It is the law that governs what happens when you are presented with a single, arbitrary quantum particle, a qubit whose delicate superposition of states is a complete mystery to you. The universe forbids you from building a machine that can look at that particle and produce a second independent particle in the exact same unknown state. To learn its identity is to shatter its identity. To measure is to disturb. And in that disturbance, the original pristine state is lost to the cosmos forever. Here, in this very specific prohibition, lies the pivot. Here is where the entire narrative of limitation inverts itself, blossoming into a story of empowerment. For centuries, human security has been a cat-and-mouse game based on complexity. We build a lock, someone learns to pick it. We create a mathematical cipher, someone builds a faster machine to break it. Our secrets have always been protected not by fundamental laws, but by the temporary technological or intellectual superiority of the protector over the attacker. We hide information behind walls of mathematical difficulty, hoping the walls are high enough and thick enough to withstand the siege until the information is no longer valuable. But what if there were a different way? What if we could build a vault whose security was not contingent on the cleverness of its engineer, but was instead guaranteed by the very laws of physics that govern existence? This is the profound promise of the No Cloning Theorem. It is not a cosmic rulebook telling us what we cannot do. It is the universe itself offering to act as our ultimate guardian of secrets. This seemingly abstract principle finds its most stunning and immediate application in the field of quantum cryptography, specifically in a revolutionary protocol known as quantum key distribution, or QKD. To understand its power, we must first appreciate the fragility of our current digital world. Nearly all of our secure communication, our banking, our private messages, our government secrets, relies on a system called public key cryptography. It works because of a mathematical trick. It's incredibly easy to multiply two enormous prime numbers together, but it is monumentally difficult to take that resulting product and figure out which two primes were its original factors. Our security is based on this asymmetry of effort, but monumentally difficult is not the same as impossible. A sufficiently powerful computer, perhaps a future quantum computer, could potentially shatter these mathematical walls, rendering all of our past, present, and future secrets utterly transparent. Our entire digital civilization rests on a foundation of sand, on the hope that no one will build a powerful enough shovel. Quantum key distribution replaces this foundation of sand with the bedrock of physical law. The goal is simple for two parties, whom we have traditionally called Alice and Bob, to securely share a secret key, a random string of ones and zeros, which they can then use to encrypt and decrypt their messages. In the classical world, they would have to send this key via a trusted courier or use the mathematical methods we just described. But in the quantum world, they can create a key whose security is absolute. They do this by encoding the bits of their key onto the quantum states of individual photons, the fundamental particles of light. Imagine Alice has a special laser that can send out one photon at a time. For each bit of her secret key, she can choose to encode it onto the photon's polarization, the axis upon which its electromagnetic field oscillates. For a 0, she might polarize a photon vertically. For a 1, she might polarize it horizontally. Or using a different basis, she could encode a 0 as a 45-degree diagonal polarization and a 1 as a 135-degree diagonal polarization. Alice now sends a stream of these individually encoded photons to Bob through a fiber optic cable or even through open air. Bob on his end has a detector that can measure the polarization of each incoming photon. But here is the crucial quantum element. To measure the polarization, Bob must also choose a basis, either the rectilinear basis, vertical and horizontal, or the diagonal basis. If Alice sent a vertically polarized photon and Bob measures it in the correct rectilinear basis, he will register a 0 with 100% certainty. But if he chooses the wrong basis, the diagonal one, to measure that same vertically polarized photon, the laws of quantum mechanics dictate that the outcome becomes completely random. The photon will be forced to choose one of the two diagonal polarizations, 45 or 135 degrees, with a 50% chance for each. His measurement irrevocably alters the photon's state, collapsing its original definite polarization into a new one, aligned with his measurement choice. The same principle applies to all combinations. When their bases match, the communication is perfect. When they mismatch, the result is noise. After Alice has sent her entire stream of photons, she and Bob get on a classical public communication channel like a telephone call that everyone can hear, and they perform a startlingly simple act of reconciliation. They do not reveal the secret key bits they sent or received. Instead, for each photon, they reveal only the times basis, times they used to send or measure it. For all the photons where they happen to choose the same basis, they know their results must match. These bits form the raw material for their secret key. For all the photons where their base is mismatched, they know the results are random and meaningless, so they simply discard them. After this public discussion, Alice and Bob are left with a shorter but now perfectly shared secret random key. And it would seem at first glance that their communication is secure, but we have forgotten about the ever-present threat, the eavesdropper, whom we shall call Eve. In a classical system, Eve's strategy is simple and devastatingly effective. She could tap into the fiber optic cable, intercept the signal, read the key, copy it down, and then send a perfect replica of the signal on to Bob. Alice and Bob would be none the wiser, their secure communication completely compromised from the very beginning. But Eve is now operating in a quantum world, and she is about to collide head-on with the No Cloning Theorem. Her classical instincts are now useless. She intercepts one of Alice's photons, a single quantum of light, carrying a secret she desperately wants to know. She cannot simply copy it. The universe has forbidden her from creating a perfect replica of this unknown quantum state. Her only option is to try and measure it herself. But the moment she does, she is caught in the same quantum trap as Bob. She must choose a basis, rectilinear, or diagonal. Let's follow Eve's dilemma. Suppose Alice sends a vertically polarized photon, intending it to be a 0 bit. Eve intercepts it. She has no idea what basis Alice used. She has to guess. Let's say she guesses correctly and uses the rectilinear basis. She measures the photon, registers a 0, and now she knows the bit. She can then generate a new photon, polarize it vertically, and send it on to Bob. In this specific instance, her presence goes completely undetected. But Eve will not always be so lucky. 50% of the time her guess will be wrong. Suppose Alice sends that same vertically polarized photon, but this time Eve incorrectly chooses the diagonal basis to measure it. The instant her measurement device interacts with the photon, its original state is destroyed. The measurement forces the photon into either a 45-degree or 135-degree state completely at random. Eve records a random bit, and then attempting to cover her tracks, she sends a new photon with that new incorrect diagonal polarization on to Bob. Later, when Bob receives this altered photon, he too must measure it. If he happens to use the same diagonal basis as Eve, he will measure the bit Eve sent, not the one Alice originally intended. But if he uses the rectilinear basis, the one Alice originally used, his result will times again times be random. The act of Eve's measurement has introduced a fundamental error, an indelible quantum scar on the communication channel. Her attempt to secretly observe the information has irrevocably corrupted it. This is the theorem's ultimate power. It transforms the act of eavesdropping from a passive, invisible act into an active, noisy, and inescapably clumsy one. Eve, by her very nature, becomes a bull in a quantum china shop. The discovery of this unavoidable disturbance is the final brilliant stroke of the protocol. After Alice and Bob have compared their bases and identified the bits that should form their secret key, they perform one last check. They publicly sacrifice a small random portion of that key, comparing the actual bit values. If the channel was secure, their bits should match perfectly. But if Eve was listening, her constant guessing of measurement bases will have introduced a significant number of errors into the key, an error rate that Alice and Bob can easily detect. They will see a discrepancy that should not exist. The moment they see it, they know their communication has been compromised. They do not know what the key is, but that no longer matters. They know that times, Eve knows times something about it, and so with absolute certainty of a breach, they discard the entire key and begin the process again, perhaps waiting until the channel is clear. Eve's attempt to learn the secret has resulted only in the secret's destruction. This is not a system based on hope, it is a system based on a guarantee. The security is underwritten by the fundamental architecture of reality. Any attempt to intercept the key leaves a fingerprint, a trace of disturbance that cannot be hidden, cannot be erased, and cannot be avoided. The No Cloning Theorem, that great cosmic no, has become the most powerful yes in the history of cryptography. Yes, you can have a truly secret conversation. Yes, you can be certain that you are alone. It has transformed a perceived flaw in the universe into its most profound security feature. The very thing that prevents us from perfectly duplicating a quantum state is the very thing that guarantees its privacy. The fragility of a quantum bit, its tendency to be disturbed by observation, is not a weakness to be overcome, but a strength to be harnessed. We stand here in the shadow of this revelation and see the world differently. The universe is not a passive canvas on which we paint our technologies. It is an active participant with rules and behaviors that can be integrated into our designs in the most profound ways. We have taken a law that seemed to close a door and used it to build an unbreachable fortress. This principle of turning a fundamental physical constraint into a technological asset echoes far beyond secure communications. It suggests a complete rethinking of our relationship with the quantum world. If this one prohibition, the inability to clone, contains within it the secret to perfect security, to what other wonders might be lurking within the other strange and counterintuitive laws of this realm? What new capabilities might be enabled by the very impossibility of knowing a particle's position and momentum at the same time? What technologies could be born from the absolute certainty of entanglement's strange connection? The downward path has led us to a summit of unimagined security. Now we must ask, where do the other forbidden paths of the quantum world lead? And so the theorem stands, an immutable law carved into the bedrock of reality, a cosmic declaration that the soul of a quantum state, its delicate probabilistic ephemeral existence, cannot be counterfeited. For decades, this profound limitation felt like a door slammed shut, a boundary drawn around our ambitions. It seemed to tell us what we could never do. But the universe is rarely so simple. Its prohibitions are often subtle invitations, its limitations the very architecture of a deeper, stranger magic. What if this absolute ban on copying wasn't a barrier at all? What if it was the very thing that made the impossible possible? What if the only way to move a ghost was to promise the universe that you would never ever let it have a twin? This is the story of how a cosmic no became the ultimate yes. It is the story of quantum teleportation. The very word conjures images of science fiction of bodies dematerializing in one place and reappearing atom for atom in another. But the reality is both less and infinitely more profound. We cannot teleport matter, not in the way we dream. We cannot send a person across a room, let alone the stars. What we can do is something far more delicate, far more fundamental. We can teleport times information, asterisk. Not just any information, not the simple ones and zeros of a classical computer, but the complete, indescribably complex quantum state of a particle. We can transfer its very essence, its identity, its superposition of all possible realities from one location to another, without that particle ever traversing the space in between. To achieve this feat, a feat that seems to mock the very fabric of space-time, we must make a Faustian bargain with the universe, a pact enforced by the No Cloning Theorem itself. The price of moving a quantum state is the absolute, irrevocable destruction of the original. To understand this extraordinary process, you must imagine two scientists, our familiar Alice and Bob, separated by a vast distance. Long before their experiment begins, they prepare their essential tool, their conduit for this quantum magic. They create a pair of particles, photons for instance, and entangle them. This process, which we have seen, is a cornerstone of the quantum world, forges an unbreakable, instantaneous link between them. One particle is sent to Alice, the other to Bob. They now share a single distributed quantum reality. Alice's particle and Bob's particle are no longer individuals. They are two halves of a single whole, a unified system connected by what Einstein famously called spooky action at a distance. This entangled pair is their resource, their private quantum channel waiting to be used. Now the real experiment can begin. Alice is given a third particle, let's call it particle C. This is the particle whose state she wants to teleport to Bob. The state of particle C is a complete mystery even to Alice. It might be in a definite spin state, or it might exist in a complex superposition of many states at once. According to the laws we have explored, for her to know its state with perfect certainty, she would have to measure it an act that would collapse its wave function and destroy the very superposition she wishes to send. The No Cloning Theorem looms large, reminding her that she cannot simply look at the particle, record its properties, and email them to Bob. The information is unknowable and uncopyable, So she does something extraordinary, something that feels like a logical paradox. She takes her unknown particle C and performs a joint measurement on it times and times her half of the entangled pair. This is not a simple observation. It is a sophisticated quantum interrogation known as a Bell state measurement. Think of it as forcing her two particles, the message and her half of the conduit, into a conversation. She is not asking particle C, "What is your state?" that is forbidden. Instead, she is asking the combined system a different kind of question. How are you two related to each other? The result of this measurement does not reveal the secret state of particle C. Instead, it gives her one of four possible outcomes, four classical bits of information that describe the relationship, the quantum correlation between the two particles she holds. But in the very act of asking this question, in the instant she receives her answer, something dramatic and irreversible happens in her lab. The interaction scrambles the states. The original precious quantum state of particle C is annihilated. It is gone forever, its delicate superposition shattered by the measurement. She has paid the price. She has sacrificed the original. And in that exact same instant, hundreds or thousands of kilometers away, something miraculous occurs in Bob's laboratory. Because his particle was entangled with Alice's, the measurement she performed on her particles has an immediate, instantaneous effect on his. His particle, which was in a state of complete indeterminacy, instantly changes. Its state morphs it, contorts it, becomes a new, definite but time-scrambled times version of Alice's original particle C. The information has, in a sense, already arrived. The quantum part of the transfer is complete. Yet the message is locked, encrypted by the randomness of Alice's measurement. Bob has a chest, but he has no key. He holds a particle that contains the soul of Alice's original, but its form is twisted, unrecognizable. The teleportation is not yet complete, because while the quantum connection is instantaneous, the final step is bound by the familiar speed of light. Now Alice must do something completely mundane. She picks up a telephone or sends an email, or flashes a laser pulse across the distance to Bob. She sends him the classical information from her measurement, those two simple bits that represent one of four possible outcomes. This is the key. This is the instruction manual. It travels no faster than any other message we could send. When Bob receives this classical key, he finally knows how times his particle is scrambled. If Alice sent him a 00, he knows his particle is in one configuration. If she sent a 01, it's in another. The key tells him precisely which of four specific quantum operations, which tiny precise nudges he needs to apply to his particle to unlock it. He applies the correct transformation, a phase shift, a bit flip, and in that moment the transformation is complete. His particle becomes a perfect, flawless replica of the particle Alice once held. Same superposition, same entanglement history, same quantum identity. He now possesses the original state. He doesn't have a copy. He has the time state resurrected in a new body in a new location. This is the profound beauty of the No Cloning Theorem in action. It is not a rule that prevents teleportation. It is the rule that times guarantees times its integrity. The universe allows this seemingly impossible transfer of information only on the absolute condition that the original is sacrificed in the process. You can move a quantum state, but you can never have it in two places at once. The theorem acts as the ultimate cosmic conservation law, not for energy or momentum, but for quantum identity itself. It is a sacramental act of transfer, not a mechanical act of duplication. The original entity undergoes a kind of death, and its exact state is reborn elsewhere. There is no moment where two versions exist. The universe's ledger remains perfectly balanced. This dance of entanglement, measurement, and classical communication demonstrates that the theorem isn't just a mathematical curiosity. It is a dynamic operational principle that shapes what is possible at the deepest level of reality, enabling one of the most astonishing technologies we have ever conceived. If this theorem provides the foundational logic for transferring a single quantum state, it casts a far more imposing shadow over our grandest computational dream, the quantum computer. Here, the theorem's prohibition on copying feels less like a clever rule for a magic trick and more like a potentially fatal flaw in our engineering. We are trying to build machines of unimaginable power, by harnessing the most delicate and fragile aspects of reality. Our processors are not built from robust silicon switches, but from qubits, individual atoms, photons, or superconducting circuits that exist in a state of ethereal superposition. They are crystal sculptures made of smoke whispers in the quantum wind, constantly threatened by the slightest interaction with the outside world. A single stray photon, a tiny fluctuation in a magnetic field, a whisper of thermal energy, any of these can cause a qubit to decohere, for its wave function to collapse, and its precious quantum information to be lost forever in the noise of the classical world. This is the great enemy of quantum computation error. In the classical computers that power our world, the solution to error is beautifully simple and brutally effective redundancy. If a bit of information is important, we don't just store it once. We make 3, 5, or 7 copies. We store them in different places. If one of these bits flips from a 1 to a 0 due to some cosmic ray or hardware fault, the computer simply takes a majority vote. The others still read 1, so the error is detected and instantly corrected. This principle of redundancy and copying is woven into the very fabric of our digital infrastructure. It is how we trust our bank accounts, our communications, our entire civilization. But in the quantum realm, this lifeline is severed. The No Cloning Theorem stands as a celestial guardian, declaring with absolute finality you cannot make a backup copy of an unknown quantum state. You cannot protect a fragile qubit by creating duplicates. The very act of trying to read the qubit to copy it would destroy it. How then can we ever hope to build a reliable quantum computer? How can we perform calculations involving millions of fragile qubits for millions of steps if we have no way to guard them against the ceaseless storm of decoherence? Challenge seemed insurmountable. It was as if we were asked to build a skyscraper out of soap bubbles in the middle of a hurricane. For a time, many believed it was the end of the road, that large-scale quantum computers would forever remain a theoretical dream shattered by the practical realities of a noisy universe and the unyielding law against cloning. But the ingenuity of the human mind when faced with a fundamental law of nature does not retreat. It finds a way to turn the law to its advantage. The solution when it came was as elegant and counterintuitive as teleportation. It was a complete reinvention of the idea of redundancy itself. It is the concept of quantum error correction. If you cannot copy the state times of a qubit, perhaps you can protect it by hiding its information, by smearing its identity across many other particles. Instead of making multiple copies of one qubit, you would use a collection of physical qubits to encode a single, more robust logical times qubit. Imagine you have a single precious piece of quantum information. You cannot write it down on multiple pieces of paper. Instead, you could encode it into a pattern of relationships. You take, for instance, 7 physical qubits, and through the magic of entanglement, you weave them together into a single, complex, unified state. Your secret information is no longer held by any single one of them. It has become a non-local property of the entire system. It exists in the subtle correlations in the ethereal consensus between all 7 particles. This protected abstract entity is your logical qubit. The 7 physical qubits are its guardians, its servants. Now the storm of decoherence can strike. A stray magnetic field might flip the spin of the 3rd physical qubit. In a classical system, this would be a fatal error. But here something wonderful happens. The error disrupts the delicate pattern of entanglement. The relationships between the qubits are altered in a very specific telltale way. The trick is to design a system where we can check on these relationships without ever looking at the secret they are protecting. We can perform collective measurements on the guardian qubits, not to ask them what information they hold, but to ask if they are still in agreement. Are their parities, their collective properties, still aligned in the way they are supposed to be? These measurements, called syndrome measurements, are designed to be blind to the actual logical state. They act like sentinels patrolling the perimeter. They can't see the treasure in the vault, but they can see if a window has been broken. If the syndrome measurement comes back with a specific result, it acts as an alarm. It tells us 2 things. First, that an error has occurred, and second, precisely times what times of error it was, and times which times of the 7 physical qubits it affected. It might tell us a bit flip error happened to qubit number 3. It does not and cannot tell us what the logical state of the information was. The secret remains safe. Once the syndrome is diagnosed, the fix is straightforward. We know exactly what went wrong and where. We can apply a targeted quantum operation, a precise pulse of energy exclusively to the afflicted third qubit, reversing the error and restoring it to its proper place within the entangled collective. The delicate pattern of relationships is healed. The integrity of the logical qubit is restored. And all of this was achieved without ever learning, copying, or destroying the fundamental quantum information it was built to protect. This is the genius of quantum error correction. It is a system of redundancy that doesn't rely on duplication but on distribution. It is a way of making information robust, not by making it louder, but by making it shared, non-local, and collectively resilient. It is a profound acknowledgement of the No Cloning Theorem, working with the grain of the universe instead of fighting against it. The theorem, which once seemed to be the greatest obstacle to quantum computing, has become its most important architectural principle. It forced us to abandon our simple classical intuition and to develop a far more sophisticated and powerful understanding of information. It demanded that we invent new ways of thinking to encode data, not in single entities, but in the ghostly connections between them. Building a fault-tolerant quantum computer is now a grand engineering challenge of scaling these error-correcting codes using dozens, hundreds, or even thousands of noisy physical qubits to create a single near-perfect logical qubit. The path is monumentally difficult, but the theorem has shown us that it is not impossible. It has shown us that the universe's most stringent laws are not just limitations. They are signposts pointing us toward a deeper, more elegant, and more quantum way of building our future. The very rule that forbids the simple act of copying has become the foundation upon which we are constructing the most complex machines ever imagined. It ensures that to build with the quantum world, we must first learn to think like it. But what does a universe that operates on such principles truly mean for our understanding of reality itself? What happens when these machines finally come online, built upon a logic that so deeply defies our own? And so we arrive at the quiet aftermath of a profound revelation. Our journey began with a very human desire, a dream as old as art and language itself, the desire to create the perfect copy, to preserve a fleeting moment, an idea, a state of being with absolute fidelity. We envisioned a future where information could be duplicated without loss, where complex quantum systems, the very building blocks of a new technological age, could be backed up and shared as easily as a digital photograph. We chased a phantom only to collide with a law etched into the deepest foundations of the universe, a law that felt at first like a cosmic denial, a door slammed shut, a final, definitive, and perhaps disappointing no. The No Cloning Theorem, in its elegant and devastating simplicity, told us that our quest was impossible. It declared that an unknown quantum state, this delicate tapestry of probability and potential, could not be perfectly replicated. To even attempt the act to measure its properties with the intent to copy them was to destroy the very essence of what you sought to preserve. The act of observation was an act of transformation. The original's fragile superposition, its intricate web of possibilities, would collapse into a single mundane reality, leaving its soul, its quantumness, forever lost. It seemed like a fundamental limitation, a cruel joke played by nature on our burgeoning quantum ambitions. It was the universe telling us that some things are by their very nature singular and ephemeral. But here, in the echo of that initial verdict, we have discovered the most beautiful of scientific truths, that the universe's greatest limitations are often its most powerful gifts in disguise. The wall we ran into was not a prison wall, it was the load-bearing wall of a new reality. The very principle that denied us the trivial ability to copy a qubit became the absolute guarantor of its sanctity. The universe, in forbidding perfect replication, had inadvertently handed us the key to perfect security. It had given us a law that could not be bent, broken, or bypassed because it is woven from the same fundamental logic as space-time and causality. It is not a rule enforced by some external agent. It is a consequence of how reality itself is structured. Consider the world of secrets, a world that has, until now, relied on the complexity of mathematical puzzles. We build cryptographic walls out of ever larger numbers, hoping that our adversary's computational power is insufficient to tear them down. But this is always a temporary truce, an arms race against ingenuity and processing speed. A clever algorithm, a faster computer, or the sheer brute force of time can eventually lay any classical secret bare. The security is conditional based on assumptions about difficulty, but the No Cloning Theorem offers something else entirely. It offers a security based not on human cleverness but on the laws of physics. Imagine two parties wishing to share a secret key, the foundation for an unbreachable code. They transmit this key not as classical bits of ones and zeros, but as a stream of single photons, each prepared in a specific quantum state, a delicate polarization, a fragile spin. Now picture an eavesdropper, a spy attempting to intercept this transmission. In a classical world, this is trivial. You tap the line, read the signal, and pass along a perfect copy, your presence utterly unknown. The original message is undisturbed, the recipients none the wiser. But in the quantum realm, the eavesdropper faces an impossible dilemma, a dilemma authored by the No Cloning Theorem itself. She cannot simply copy the quantum state of the photon and send the original on its way. The theorem forbids it. Her only choice is to interact with it directly, to perform a measurement to determine its state. Yet the moment she does, the moment her probe touches that fragile quantum reality, she forces it to choose. The photon's superposition of states collapses its quantum identity, irrevocably altered. She may learn its secret at that instant, but the damage is already done. The photon that continues on its journey is now a forgery, a clumsy classical imitation of the pristine quantum original. It carries upon it an indelible scar of her observation. When the intended recipient receives this altered photon, the forgery is immediately obvious. Their own measurements will not align with the senders in the way they should. The statistical correlations, the beautiful ghostly dance of quantum probability that they expected will be broken. The conversation will show signs of interference, a telltale static introduced into the quantum channel. The secret has not been stolen, it has been shattered. The very act of listening has destroyed the message, sounding an alarm that cannot be silenced. The No Cloning Theorem has transformed the information itself into its own watchdog. It has deputized the laws of physics as the ultimate security guard, a silent, incorruptible sentinel standing watch over every quantum transmission. This is not a promise of future technology. It is the reality of quantum key distribution networks already crisscrossing our globe, transmitting data protected by a shield of physical law. The theorem ensures that if a message arrives untouched, its security is not a matter of probability but of certainty. It is a form of privacy so absolute that it feels alien to our classical intuition, a privacy gifted to us by the very law we once saw as a restriction. The universe, it seems, values a good secret, and it has built the ultimate protection for it into the very grammar of existence. The dream of the perfect copy was sacrificed for the reality of the perfect secret. This guardianship extends far beyond mere communication, reaching deep into the heart of the quantum computer. Inside these revolutionary machines, information exists in its most potent and delicate form. Qubits linked in the ghostly embrace of entanglement explore a vast, multidimensional landscape of possibilities simultaneously. This quantum parallelism is the source of their incredible power, but it is also the source of their profound vulnerability. A single stray interaction, a whisper of environmental noise, can cause this entire intricate structure to decohere, collapsing the calculation into a cascade of errors. The computation is a tightrope walk performed by a phantom over a bottomless chasm. In this delicate environment, the No Cloning Theorem serves as a crucial internal shield. It prevents the surreptitious amplification of errors. If a small error, a slight perturbation in a single qubit, could be copied and spread throughout the system, it would quickly overwhelm the entire computation like a virus replicating uncontrollably. But the theorem stands in the way. An error, being a deviation from the intended quantum state, is itself a form of quantum information, and as such it cannot be cloned. It remains localized, an isolated flaw that sophisticated quantum error correction codes, themselves designed with the theorem in mind, can then detect and contain. It ensures the integrity of the process, guaranteeing that the quantum state evolving inside the machine remains a singular, coherent entity. You cannot simply tap into a quantum calculation to see how it's going without derailing it entirely. The computer's internal state is unknowable until the final answer is measured. This creates a black box of immense power protected from prying eyes by the same law that protects a quantum key. It ensures that the vast, ghostly computation happening within the machine's core is for its eyes only, a private conversation between qubits, mediated by the laws of probability. Without this fundamental restriction on replication, the very notion of a stable, large-scale quantum computer might have remained an impossible dream, forever dissolving into a sea of amplified noise. The limitation once again reveals itself as a cornerstone of stability, the silent architect of computational integrity. As we stand back and survey the consequences of this single, elegant principle, we realize that its implications ripple outwards, far beyond technology, touching the very definition of information, identity, and reality. For millennia, we have operated under a Platonic ideal of information that an idea, a number, a story is an abstract entity separate from its physical vessel. The words on this page are merely a representation of the meaning they carry. You can copy the words endlessly, and the core information remains unchanged. It is promiscuous, able to be embodied in ink, in pixels, in sound waves, without losing its identity. This is the classical view. The No Cloning Theorem challenges this ancient assumption head-on. It suggests that at the fundamental level, quantum information is not abstract. It is inextricably and profoundly fused with its physical carrier. A qubit is not just a vessel times for times a state. It times is times its state. Its identity, its unique superposition, its entanglement with other particles is a singular property of its existence in a specific place and time. To copy it is not just technically difficult, it is metaphysically impossible, for you would be trying to create a second instance of a uniquely singular identity. You cannot clone a qubit for the same reason you cannot have two separate distinct instances of the exact same now. This gives every particle, every quantum system, a kind of inviolable individuality. My configuration of atoms is at the classical level replicable in principle, but the precise unknown quantum state of all my constituent particles is a unique signature, a cosmic watermark that cannot be forged or duplicated anywhere else in the universe. This law is the universe's ultimate statement on originality. It screams that at the very bottom, reality is not a mass-produced commodity. It is a collection of unique, uncopyable individuals. This profound idea forces us to ask deeper questions. If a quantum state cannot be copied, what does that mean for the fate of information in the most extreme environments imaginable, like the event horizon of a black hole? The famous black hole information paradox wrestles with this very issue. When matter falls into a black hole, its unique quantum information seems to be lost forever, a violation of quantum mechanics. But if that information can't be cloned, it couldn't have been copied on the Hawking radiation streaming away from the black hole either. The No Cloning Theorem stands as a critical constraint in this cosmic debate, to a key piece of the puzzle in our quest to unify quantum mechanics and gravity, reminding us that even at the edge of oblivion, the rules of information and individuality hold sway. Our journey ends where it began, staring into the heart of the quantum world. But we are not the same observers who started this quest. We came seeking a tool for duplication, for control, for the power to replicate and preserve. Instead, we found something far more valuable. We discovered a fundamental truth about the universe, that it is built on a foundation of uniqueness, that the fragility of a quantum state is also the source of its strength, that its inability to be copied is the very thing that makes it trustworthy. The No Cloning Theorem is more than just a footnote in a physics textbook. It is a piece of cosmic poetry. It is the quiet guardian of privacy in a universe of quantum whispers. It is the guarantor of integrity in the heart of our most powerful future machines. And it is a constant, humbling reminder that we are not masters of a predictable clockwork reality that bends to our every whim. We are participants in a far stranger, more subtle and more beautiful cosmos than we ever imagined. A universe where some things, a secret, a calculation, a fleeting state of being, are meant to be one of a kind. A universe that does not permit forgeries, ensuring that every quantum interaction, every particle and every moment is and will forever remain a true original.